Hi, welcome friends into chapter 7. We're going to be talking about graphing systems of equations, and this is an important topic because when you have systems of equations, you're going to find that you can solve, being able to use systems of equations, you can find that you can solve lots of word problems. So we'll see that a little bit later, and you'll also see this in Algebra 2 too, and on standardized tests. So it's just a good thing to know. So, a couple of vocabulary items that we need to keep in mind. So, systems of equations, the way we're going to talk about them is basically you're going to have two equations, something maybe like, nope, not that pen. You're going to have something like, let's say, 2x plus 4y is equal to 7, and then maybe negative 2x plus y is equal to 9. And what you're looking for is an xy that satisfies both of these linear equations. So that's a system of equations. It's just having more than one equation where you're looking for a solution that works in all of those equations. Notice we've got two variables, two equations, and two unknowns. And so what you're also going to see is the more variables you have, the more equations you want, because then you can solve it. And that's just kind of a little thing. All right, so now we have these words that are a little bit trippy. Not really trippy, but they're kind of hard to keep in mind, and I think we need a visual for it. So I did copy this from the textbook. Take a look. If you have, so now when we're looking for these solutions, what we're generally going to do is graph the two linear equations. So if I were looking for a solution for these guys, I'd graph these two and see what point x and y intersect in. So because we're graphing, the graphical representation of the next vocabulary words will be helpful. So sometimes you'll graph the two lines and you'll get intersecting lines. When you have lines that intersect, you have exactly one solution, and that is considered consistent and independent. Both consistent and independent. Sometimes you'll find yourself graphing the two lines, right? And instead of having two separate lines, you'll have the same line appear once. So then you'll graph one, you'll be like, ooh, look at that. And then you'll graph the next one, you're like, wait a minute, it's exactly the same line. So if you graph the two lines and you happen to find that they're exactly the same line, the number of solutions are infinitely many because there's infinitely many points where they agree. That is considered consistent and dependent. Consistent and dependent. Look at the difference between these two. Consistent and independent. Consistent and independent. Consistent and dependent. Dependent seems like you've got the same graph, right? Dependent means like this graph depends on the other graph. They're the same line, so they're dependent. These two lines are independent. They're different. They are different. And so that's one way to help you decide what's going on. And then sometimes you're going to graph these lines and you'll find that one line does this and the other line does this and they never touch. So there is no solution. So when you find that you have parallel lines, you have no solution in terms of the system of linear equation, and that system is considered inconsistent. And so I think that kind of helps with this terminology up here. This is a really nice graph to copy down, so I would do that if I were you. So here we are in example 1, and what we're looking for is the number of solutions based on this little graph that we talked about up here, that little graphic rather. We're going to look for the number of solutions, and fortunately for us, they actually graph the equations, so life is kind of good. Let's see what we can do. Use the graph at the right to determine whether each system has no solutions, one solution, or infinitely many solutions. So the first thing I'd like to do is let's take a look at A. Notice that the equation, is the equation written there perfectly? Yeah, there it is. So y is equal to negative x plus 5, and y is equal to x minus 3 is here. And so we see that yes, there is one solution. So it has one solution, and that's it. And that one solution would be consistent and independent, just for kicks and giggles. And then over here, y is equal to negative x plus 5. So we're looking at this guy. And 2x plus 2y is equal to negative 8. Where's that? 2x plus 2y equals negative 8. I'm going to highlight those so I can kind of get an idea. Nope, that's not highlighting. I'm going to highlight those so I can get an idea of what it looks like. So here's this one, 2x plus 2y, and here's this one, negative x plus 5. And I noticed that those bad boys are indeed parallel. So there is no solution because I have parallel lines, right? And we would say that that's an inconsistent system. It's inconsistent. And finally, we've got this same 2x plus 2y is equal to negative 8. And we're going to look at y is equal to negative x minus 4, which is the same line. Dun, dun, dun. And so we have infinitely many solutions because every point is a solution because it's the same exact line, and we know that it is consistent but dependent. So here we are with example 2, and I'm going to solve this system of equations by graphing. We're going to graph each system of equations, then we're going to determine whether the system has no solutions, one solution, or infinitely many. If the system has one solution, we're going to name it. All right, so let's go ahead. These are beautifully put in slope-intercept form, so it's totally easy for me to graph. So I'm going to graph this first equation. Let me highlight it in red so we can distinguish. Okay, so let's go ahead and graph the first one. So what I'll do is I will start with a positive 8. 1, 2, 3, 4, 5, 6, 7, 8, which is my y-intercept. Let me make sure I got that right. 1, 2, 3, 4, 5, 6, 7, 8. Good. And my slope is negative 1, so that's down 1 to the right 1, down 1 to the right 1, down 1 to the right 1. You guys see where this is going. And so this is my line. Let me see if I can draw something that resembles a line, nice and straight. I got a little bit crazy. You saw that went right over here. Okay, so there we go. I'm going to just do that because I can't really do a really good job here. All right, and this is honestly, I know I'm kind of being a little terribly sloppy, but what I want you to see is that the reality is this is why this isn't the best method. And so we're going to learn some other methods in the upcoming chapters. So let's go ahead. 1, 2, 3, 4, 5, 6, 7. So we start down at negative 7 and we go up 4 because my slope is 4. Up 1, 2, 3, 4 to the right 1. Up 1, 2, 3, 4 to the right 1. Up 1, 2, 3, 4 to the right 1. So something is going to give here, right? So somewhere here, these guys intersect. And the fact is, you're looking at it and you're like, what kind of nonsense did you just do there? Now, obviously, if I were using grid paper and a pencil and a ruler, I'd have a better looking line. So I'm going to graph this elsewhere. So I used this super cool Desmos app, and I graph both of those equations, and I see that those two lines cross at 3, 5. Now, I believe you could have drawn a really nice graph like that too, like they have here. But the fact of the matter is, the question arises, what if the answer is a decimal? What if your graphing isn't that neat? What if it's like 2.1 and 5.7? How would you determine that? And so you'll see that it'll be really interesting for us to come up with different techniques to do this algebraically. So Desmos, as we said before, gave us the answer to be positive 3, 5. And so that's my solution. And so I have one solution. That's what that tells me. I've got one solution. Let's see if we can try this other guy. So since I'm required to graph these guys, I'm going to solve for y with each of these equations. So I get 2y, I'm subtracting x on both sides, is equal to negative x plus 5, and then I'm going to divide both sides by 2, and I get y is equal to negative 1/2 x plus 5 over 2. So that's me reworking the first equation. I'm going to do the same thing over here. I'm going to throw the negative 2x onto the other side, and I'm going to divide everything by 4. So I get y is equal to negative 2 over 4x plus 2. y is equal to negative 1/2 x plus 2. And already what I'm noticing is something that we talked about in the last problem, right? Do you guys, not the last problem, but the last chapter, notice that both of the slopes are the same. When you have two lines with the same slope and different y-intercepts, this one's 5/2 and this one's 2, two lines, oh, I don't think that's right actually. I think I had to divide everything by 4. So this should be 1/2. Thank you guys for finding my mistake. So this y-intercept is 5/2 and this one is 1/2. But notice that the two slopes are the same. When you have two lines with the same slope, those lines are parallel. And I spent all this time making this. I'm going to actually take this over and graph them on Desmos like we did last time. So here we see the two equations are here. Let me change the color on this one, make it a little bit more distinct. So you can see the two equations are indeed parallel, and I didn't even write them in the form that I saw for y. I just wrote them exactly as it was, and you can see Desmos will graph them. And so we see that we have parallel lines, and so when I go back to the problem, I can say that this equation, these two have no solution because they have no intersection. And that's the gist of our lesson for 7-1. So basically, you're going to be graphing linear equations and you're going to look to see if you get one solution, infinitely many, or no solution at all. And that's how we're going to proceed with systems of linear equations for this section. I can't wait to talk to you about some really cool algebraic methods, which are pretty awesome. All right, guys, I look forward to talking to you soon. Take care and have a good day. Bye-bye.